When we want to represent points on a plane mathematically, we tend to do that using vectors. So things like this here, when x and y are real numbers, and x tells you how far to go across from a particular point, usually called the origin, and y tells you how far to go up and down from that particular point. And the key property that these vectors have is that if you have two of them and they're equal, so x, y equals z, w, well, that happens if and only if x is equal to z, and y equals w. And this property is called the ordered pair property. And what we're going to do is describe a similar construction where the entries in our ordered pairs can come from any set, so not just from the real numbers. So what an ordered pair is, well, an ordered pair which I'm going to write as A, B, like this, so horizontally rather than vertically, is something with the property that an ordered pair AB equals another ordered pair CD if and only if A equals C and B equals D. So these things are called ordered pairs because, let's just do this in a slightly different coloured, ordered because, well, in general, AB is not equal to BA. In fact, that's only true when A equals B. So you should compare that to sets. The set containing A and B is always equal to the set containing B and A. For that reason we called sets unordered, whereas ordered pairs don't have that property. Instead, for ordered pairs, the order really does matter. Okay, so there's something to object to in this definition. I mean, the definition says an ordered pair is something with the property, and then whatever the property is. And you might reasonably object by saying, well, what exactly is it? What is an ordered pair? If you don't like these kind of definitions, too bad, unfortunately. If you really want to know how to make ordered pairs, or what kind of constructions can produce something with this ordered pair property, well, you can go and learn about formal set theory somewhere. This is not a formal set theory course, so we're not going to do it. But I think that stuff's really interesting, and if you'd like to learn further about it, if you'd like to learn more about it, you can take MATH0037 later on in your UCL career, or you can read any book about set theory. My favourite introductory set theory textbook is by Derek Goldray, and it's called Classic Set Theory. Okay, so we've now decided what an ordered pair is, or at least we've decided what the defining property of an ordered pair is, and we're then able to define this thing called the Cartesian product of two sets A and B. So if you have any two sets A and B, they could be the same, they could be different, then the Cartesian product of A and B, which we generally write as A cross B, like this, that is the set of all ordered pairs where the first element of the ordered pair comes from A and the second element of the ordered pair comes from B. So as an example, let's have an example here. So I'm going to take A to be the set 1, 2, and I'm going to take B to be the set 3, 4. And in that case, well, A cross B, which is how we pronounce this Cartesian product, A cross B consists of all ordered pairs where the first element is 1 or 2 and the second element is 3 or 4. So it would have 1, 3, 1, 4, 2, 3, and 2, 4, and nothing else. Okay, so you will notice there that we can say something about the size of the Cartesian product A cross B. So in fact, in general, not just in this case, but in general, the size of A cross B is equal to the size of A times the size of B. Okay, the point being that you can choose the first entry of your ordered pair freely from A, and you can choose the second element of your ordered pair freely from B, and for that reason the number of possible ordered pairs is the size of A times the size of B. Okay, last comment then is just that we're not restricted merely to ordered pairs. We can form ordered triples, like things of the form A, B, C, where the defining property would be that an ordered triple ABC would be equal to another ordered triple DEF if and only if A was equal to D and B was equal to E and C was equal to F. So we can form ordered triples, ordered quadruples, and so on as well.